Okay, so another problem that a student submitted to me was a problem where we're asking about a velocity of a particle moving on an x-axis. So it's probably going back and forth, something like this, right? Going back and forth, sinusoidal movement. And we're given a velocity of t is equal to minus 12 over t naught times sine of t over t naught. And we don't exactly know what t naught is, but that's not going to matter too much, as we'll see in a moment. So if we're given that, all right, so we're basically asked to find the position of the particle at t is equal to some multiple of t naught. And to get that, we're going to basically take the integral of the velocity, right? Because the integral of velocity gives you the position. But you need to be especially careful to remember your constant of integration, right? And what this constant of integration means is basically if you were to go backwards and take the derivative, right? There's a lot of different x of t's that would be able to take the derivative and get you back to this original sine expression, right? And the idea is for basically any different constants, for a bunch of different constants c, it'll work out fine. Notice that also the t naught disappears because of chain rule, right? So you're going to end up with something that looks like cosine. But the reason that they give you initial conditions, right? They're telling you that, oh, I don't know, x of 0 is equal to some value like maybe 4. Maybe let's call it 6 instead. I don't care. Right? I'm just coming up with something arbitrary. The idea is if you know the value of x naught of 6, this means that plugging in t is equal to 0 and x is equal to 6 will let you solve for c, right? So this will basically solve for c and then basically plug it back into this equation to get x of t is equal to 12 cosine of t over t naught plus some like actual number, right? It might be like 6 or 8 or some like actual genuine number. And once you have that, then you can finally plug in t is equal to like 8 t naught or whatever you're being asked to find. And you can plug that in right here and notice that the t naught is going to cancel out with this t naught. And also double check to make sure you're using radians, I think is probably a good idea. I assume this is radians rather than degrees. But yeah, this is basically the idea here, right? The big idea behind this problem is that the initial condition that they give you, x naught is equal to whatever, is going to let you find out what c is. That's the trick. That's the trick. Well, it's not even the trick. It's sort of like the point, right? But okay, that basically lets you figure out what the position is at some t is equal to whatever multiple of t naught. Now, the second part is asking you to denote an instantaneous acceleration of the particle, a of t. And remember, this is just equal to the derivative, d dt, of vt. Right? Just take the derivative of the velocity, and that gives you acceleration. So now they're asking you to evaluate some expression that looks like, whatever the initial position was. I think for my previous example, I said like 6 plus v of naught t plus a of naught t squared over 2 at t is equal to t is equal to whatever time naught they had. And for me, I just made up 8 t naught. And the idea here is that this looks a heck of a lot like kinematics, right? And kinematics is only for constant acceleration. So I haven't worked it out myself, but I would expect that once you evaluate this, you're not going to get particularly good agreement with part A because, acceleration for this problem is itself going to be sinusoidal, right? And it's going to look like that. And this doesn't look constant at all to me. And kinematics is only for constant acceleration, so there's just no reason to expect them to agree for this particular case. All right? But for part C, they're asking you to do something very similar when x is equal to 0 and t is equal to 0. And finding it when t is equal to some small value like 0.1 of t naught. Well, okay. So very similar to before, just plugging in x is equal to 0 and t is equal to 0 will again let you find a different value for c, right? So you solve for c and have an equation now. And once you have the equation, x of t is equal to 12 cosine t of t naught plus some explicit value for c, right, that you found from your initial condition. Then you can plug in some little value like 0.1 t naught or whatever you're being asked to find. Yeah? So very similar to part A, it's just a different initial condition. Instead of x naught being equal to 6, now it's equal to 0 is basically what I'm saying. So now for the very last one, part D, you're being asked to find v naught of t plus a of naught of t squared over 2 at t is equal to like some small value. And what they're claiming is that your values from parts C and D should have relatively good agreement, which is kind of funny because this is kinematics. And this is, again, a sinusoidal, right? Acceleration is still a sinusoidal thing, which is not constant at all. So it's really, really very funny why you would expect good agreement, especially when we notice that parts A and B probably did not have super good agreement, right? Well, the difference, let me just give you a hint for the difference. T is equal to 8 T naught is a pretty big value here. Like T is equal to 8 T naught means that this thing has gone multiple different, what do you call it? Multiple different phases. It's already oscillated a bunch of times in this 8 T naught time frame. But for a 0.1 T naught time frame, that's like zooming in super, super, super close, right? That's like zooming in pretty hard. And I guess the idea is when you zoom in far enough, right, you kind of lose all that sinusoidal behavior surrounding it. And suddenly, just a kinematics approximation is not that bad anymore. It's not great, but it's not that bad. Anyways, plug it in and let me know what you find, and hopefully you can kind of understand why things are a little bit nicer for parts C and D. It all comes down to how small this choice of time is going to be.